a bit about me to start with. This is pretty much me at the B-Sides after party with a bunch of other con organisers. But other than organising B-Sides Canberra, which I do with Silvio, I have a pretty long background in computer networking. So I did my electrical engineering degree at ANU back in the 90s. Worked for Telstra as a mobile phone engineer doing radio tower design and optimization. I moved into research with Telstra and then decided to move into computer networking. About probably 8 years ago, I was seconded into a security team as a network specialist. I don't know if I felt super happy about that, but here I am 8 years later, loving it and enjoying myself. So that's a bit about me. I'll get into what I'm going to talk about. So I'm going to talk about layer 2 attacks on virtual switches today. So layer 2 attacks aren't a new thing. I'm not talking about any new attacks in the layer 2 domain, but I am talking about attacking virtual switches, which is where the novelty of this talk lies. So I'm going to introduce first what virtual switches are, or what I define virtual switches to be. Then I'll talk about the layer 2 attacks, explain each attack, and tell you the result of attacking virtual switches, some mitigations options, and then I'm going to look a little bit at NSX and some of the new protocols that are coming out in the virtual domain for networks. I've only got about 2 demos, so I didn't record everything I did, and the demos may be a bit unclear, but I'll try to talk you through them. I don't have any demos attacking NSX, unfortunately, so hope you weren't here for that. So I'll start off, as I said, with an introduction on virtual switching. When it's used, where does it fit in our data center environment, and how does it interact with the rest of the network, and why would you care? So it's pretty simple. For those, most people probably do know, a virtual switch is a switch that contains virtual links. So it's implemented fully in software. It doesn't have hardware ASICs or anything. In my diagram there, the red circles the virtual switch. So it's used for communication between virtual machines, and then it usually has a hardware link out to the rest of the network. So on scale, it would be something like this, where you have multiple virtual switches, or these could be replaced by a distributed virtual switch or NSX. So in a bit more detail, this is my virtual switch at home, so really simple. You can see your VMs are attached on the left there. You can have different port groups in different VLANs, and then you usually have a physical network card that's going to connect those VMs out to the rest of the data center environment. So why do we care? Why am I looking at this? Well, there's a lot of talks on breaking out of hypervisors, getting down to the host. But maybe you've got a bad guy on your VM and he's just going to start attacking directly the virtual switch from there. So I just wanted to see the effect of that. There was some work done on this at DEF CON last year, so sort of went through what they had done and extended a bit more with a few more protocols. So they didn't look at spanning tree. I included that in mine. So the attacks I'm going to look at, and they're all well-known attacks. I didn't look at ARP spoofing because everyone does that, but I looked at MAC flooding, VLAN hopping, the 2 types, so double tagging and VTP attacks, and the spanning tree protocol, which is a pretty devastating attack. So first attack is MAC flooding. So I try to get GIFs that are relevant, but sometimes I'll just throw one in because it's funny. So for anyone who can't remember or just need a refresher on what MAC flooding is, a switch will have a CAM table where it stores information about the MAC addresses it sees, which port it's come from, and this allows it to send frames to the correct port when a frame is received, as opposed to a hub which will send out every port. So the way MAC flooding works is the attacker simply sends a bunch of frames from different MAC addresses. This fills up the CAM table, which has a fixed size. Once the CAM table's full, the switch will go into hub-like mode and start broadcasting out all the ports. So in vSwitches, like testing this against vSwitches is very similar. So there's a dotted line there. I don't know if the color's showing up well. The left is pink. That's the virtual environment. So we have our attacker on the left attacking the virtual switch with the MAC flooding. And then we have a physical switch on the outside world. So I did this against ESX, but it was already done pretty extensively at DEF CON, so I didn't record it, because it was actually really effective against most open source switches and the V switches in ESX. And there's a link there, you can read more about it. They did it pretty thoroughly. And so this is some of the stats they got. So obviously as the switch goes into broadcast mode, it starts slowing down the network. And they did it with the 2950 there as a hardware control to compare. So I'll move on to VLAN hopping. Okay, so a refresher on VLANs, for people that can't remember, it's configured as a security measure to limit the number of hosts susceptible to a layer 2 attack, so pretty much limits your broadcast domain. And VLANs will create boundaries over which those broadcasts can't cross. So in the data center environment, you may have VLAN 1, 2, and 3. And because you want your VMs to be able to migrate between hosts, you'll generally put a trunk and allow vMotion between the hosts. So the way this works on a virtual switch, and this is the ESX model, is that similar to a hardware switch, the VM will send the frame untagged. The virtual switch knows which VLAN that machine should be in and adds the tag to it if it sends it across the trunk. If it sends it locally, it's just going to keep it untagged. So then we come to VLAN double tagging. So the top frame there is the general Ethernet frame. The second frame there is the 802.1q tag, which you can see inside the frame just after the destination and source addresses. And then the second one down is the Q&Q, which is a double tagged frame where you have 2 tags in the frame. So the spec allows for this, but it does allow us to misuse VLANs. So you can see the CVE there where they say that the protocol actually allows us to bypass VLANing by putting this extra tag in. And it can be done in Yersinia. So just to talk that down a bit more in case that was a bit too quick. So this is our network with our VLANs. So a normal tagging process here, you'd have the server in VLAN 2 sends a frame to the switch. The switch acknowledges it's in VLAN 2, adds the .1q header tag 2, sends it across the trunk. The next switch will receive it, see that it was in VLAN 2, pull off the tag and send it down to any machines with ports in VLAN 2. So a special case is VLAN 1, which is known as the native VLAN. It can be changed from VLAN 1, but not many people do change it. The way it works is it's a legacy. I mean, it's implemented for legacy reasons, so it doesn't tag across the trunk. So it pretty much, when the switch receives a frame from VLAN 1, it will just send it untagged across the trunk. And then likewise, when the other side sees it, it says, well, must be native VLAN 1 and sends it out VLAN 1. So it's the native VLAN that we misuse to get VLAN hopping happening. So this is VLAN hopping. So pretty much you're on VLAN 1, the native VLAN. So some lazy engineers forgot to put you in a VLAN. You double tag it with 1 and 2. When the switch receives it, it looks at the outside tag and it says, okay, well, this is VLAN 1, this is my native VLAN, strips the tag off, sends it across thinking it's sending it untagged. The other side, it receives it and sees the inside tag, which is 2, and then forwards the frame onto any server in VLAN 2. So that's double tagging. So double tagging on virtual switches, it works if there's at least one physical switch between the VMs, as in you're heading out a trunk and back down. In Open vSwitch and Linux bridging, the DEF CON guys actually said it worked without that. I didn't get that working though. So moving on to VLAN trunking protocol, and I recorded the demo for this one at the end, hopefully it will work. So the VLAN trunk protocol is the protocol used by Cisco to enable the switches to negotiate a trunk between themselves. By default, and this is still current, Cisco will put their ports into auto mode, which means they will respond to dynamic trunk protocol requests. Yeah, so the way VTP works is the switch will just say, hey, I'm capable of trunking, will you trunk with me? And the other switch says, yeah, okay. So the way the attack works is the bad guy, who's just a server sitting there on a port that has been set to auto, will send the DTP packet and request a trunk, and the switch will bring up a trunk, and then of course you're able to communicate across any VLAN. So in the virtual world, so this is how I had it set up. I had, on the left is a 4500 running iOS XE, just modern iOS XE straight out of the box. On the right, I had my Kylie machine and a virtual switch. So I had my ESX plugging straight into a 4500. And all I do is I spin up Yersinia and send a DTP packet to try to negotiate a trunk. So this is the demo, so I hope you can see it. It's super small. So anyway, on the left is my switch I've SSH'd into, and you can see I do a show run int T13 just to see the config on that port. You can see it's got no config, but the description that I've put on there. Show int trunk, there's no trunk, so it's just sitting there on the default VLAN 1. And when I look at VLANs, I can see I've set up a prod 10 VLAN that I want to try to access. On the right is my Kylie machine, so I'm going to, which is in a VM attached to a virtual switch. So I'm going to try sending my DTP packet from my Kylie machine against the virtual switch and see what happens on the hardware switch. So coming back to the hardware switch, I do a show int trunk again, you can see that. And now there's a new trunk that's trunking all the VLANs that are on that switch. So that's my, yay, it worked. So yeah, so now I have a trunk. So there were some limitations. I thought, yeah, okay, cool, let's attack prod VLAN 10. I'm really going to own this person. But in actual fact, the trunk actually only created itself between my hardware switch, what I call VR switch, and the virtual switch. It didn't trunk all the way to the VM, so I wasn't able to create sub-interfaces and jump across to VLAN 10. But it's still, poor form in that I could possibly DOS an environment by removing trunks from that VLAN by sending DTP packets. So last layer to attack is the spanning tree protocol attack. Yeah, I found a GIF for redundancy because spanning tree is to mitigate the problems that redundancy causes in your network. Yeah, so spanning tree pretty much protects a network from loops caused by redundancy. So once you put in multiple links between switches, you start getting loops around your network, which can quickly DOS your network. So that's what spanning tree is developed for. I'll quickly talk through spanning tree to get everyone on the same path, same point on spanning tree. I'm just going to talk about basic spanning tree. So there's rapid spanning tree and per VLAN spanning tree and MST, but I'll just stick with normal spanning tree at this point. So pretty much each switch in your network has a bridge ID, which is built from your priority and your lowest MAC address. And you can see in this network I've given, it's actually cut off at the top, but the priority is the first number there. So the lowest bridge ID will become the root bridge in the network. So as an engineer, you generally do your core switch as your root bridge. So that would elect this switch here as the root bridge. Once the root bridge is elected, and this is done through sending BPDU packets. I don't know if you've ever connected to a network and had a look, you may have seen the spanning tree frames coming through every 2 seconds is default. So these BPDUs are sending through saying, I'm the root bridge, until they receive one where they think, oh no, you're the root bridge, you're better than me. Once all these are going through, adding the costs of the paths, each switch elects its root port, which is the port that is closest to the root bridge. So in this diagram, they've all elected their root ports. Once the root port election happens, the designated ports are elected, and these are, for each link, which port is closest to the root bridge. So in this situation, these would be the designated ports. Once root ports and designated ports are elected, the rest of the ports go into blocking state, and that's to stop those loops in the network. So this redundant network, once spanning tree is done with it, would look something similar to this, where there's only a single path between each switch. So there are other parts of spanning tree that I haven't covered, such as topology change notifications. This is what a switch will send if a link goes down to trigger a reconvergence of the network. So there's definitely attacks you can do by sending these that will mess up your network. And also there's the forward delay timer, which is how long a port will go into listening before it starts to forward again. So anyway, looking at how, as an attacker, we can misuse spanning tree. If you're lucky enough to get in and be able to plug into 2 switches, you can start sending your BPDUs and tell the network that you're the root bridge. So once that happens and the switches start receiving your BPDUs, there's no checking to see if you're legitimately supposed to be on the network. Everyone will start to elect their root port to face the new root bridge. And again, the designated ports will be elected, and then the rest of the links will go into blocking, and then you'll have a network that looks more like this, which means that pretty much anyone connected down on that bottom right switch is going to traverse your attacker. So bringing it back to virtual world, they say, this is a quote, that taking over root bridge is one of the most disruptive layer 2 attacks that can be done. So I don't think many people do this in their normal attack regime unless they're really bad guys. But yeah, you can pretty much pull down the network from spanning tree attacks, which I've done many times. But in the virtual world, what I've done is I've got my Kylie VM attached to my virtual switch, which then trunks through to my hardware switch. I'm going to start sending BPDUs to the virtual switch and see how it reacts to a spanning tree attack. So it should be working. So it's exactly the same environment. I have my hardware switch on the left. I've done a show spanning tree. I'm running per VLAN spanning tree, but we're only interested in VLAN 1 because that's where my VM is. You can see there it says this bridge is the root. So this switch is the root in the network at the moment. If I look at, I did a show run on T13. You can see all that's set up there is that it's a trunk. So I come back to Yersinia and I just launched the spanning tree attacks. I think I just turn a bit of logging first onto my hardware switch. So it's a bit more clear when the BPDUs start coming through. Yeah, so now I trigger the spanning tree attack. And you can see there the logging on the switch is showing that it's detecting a new root bridge on VLAN 1. So when I do a show spanning tree again on the switch, you can see there for VLAN 1 that it has a root port there on T13, which means it thinks the VM is now the root bridge for that network. So yay, attacked it again. But yeah, so that was a successful attack. So just looking through some of the mitigation options. So you can either harden the hardware switch or the virtual switch to try to mitigate some of these problems. So for the hardware switch, you can enable max security, which is normally what we do for Mac flooding, but that's tough if there's many virtual switches, so probably there's something you can do on the virtual switch instead. Disable VTP, so if you do switch port mode, trunk or access, that's not going to respond to any more DTP packets. And enable BPDU guards, so don't accept spanning tree packets from your virtual network. They're simple mitigations, but they're not on by default and not many people do them. For hardening the virtual switch, so these optional security policies that come on vSwitches, by default they were always accept, but I think maybe in ESX 5.5 they've changed it to reject, which is great. But just hop in there and make sure you shouldn't, unless you have a purpose to have your MAC address change on your VM. I mean, ESX knows what MAC address they've assigned the VM. It won't let anything but that MAC address come out of the VM. So definitely harden your... So a summary of what I've covered and the mitigation options. So MAC flooding was effective, but is easy to prevent by hopping on vSwitch and rejecting MAC address changes. VTP switch spoofing, I saw that the DTP frames were passed straight through the virtual switch to the hardware switch, so set the hardware port connected to the hypervisor to specific VLANs that you want to come up, don't leave it in auto. VLAN hopping will work if there's at least one physical switch between the VMs, so don't use VLAN 1. And spanning tree attacks, it passes through the spanning tree frames through the virtual switch to the hardware switch, so again, enable BPDU so you don't enter into any STP negotiations with any of your VMs. Okay, so for the last part, I just want to cover off a little bit on the newer virtual switches there. So I'll go through it fairly quickly. So I looked at VMware NSX. I was like, well, you know, I've looked at the normal switches. Let's have a look at what NSX can do or not do. I'll do a little intro because I built it up as fairly new. So I had to build NSX at home because I didn't want to start attacking my customer or clients' networks. I needed a minimum of 2 ESXs to be able to test some of the functionality that NSX brings. I needed a vCenter, a shared data store, and I actually needed minimum of 4 cores for the controller VMs. They require that, which my microprocessors only had 2, which was a bit of a bummer. So I had a lab already that I'd set up because I did some research on hacking the fiber channel protocol. So I reused a bunch of that, which was really good. I bought a new server with 4 cores, yay, it's good fun. I have my VMware user group membership, which is really good if you like testing and playing around with this stuff. It's like $200 a year and you get licenses for vCenter and all the new things that you need licenses for. You just can't use it in an enterprise environment. So all up is about $850 just to build NSX and test it at home. So installing it is super easy. You pretty much just download the NSX manager, deploy the VM, and it starts deploying all the components for you. You pick a distributed virtual switch that you want to deploy it to, and it just adds the modules in for the functionality. So NSX manager, it's the centralized management for NSX. It's the first component you deploy. It pretty much, as soon as you deployed it, injects a plugin into vCenter, so you get a new menu option that allows you to configure and manage NSX, and then that just goes and installs the rest of the components of NSX. So NSX controller, which is the beefy VM that needed 4 cores, it's like the brains of NSX. It stores the ARP tables, the MAC tables, the VTAPs, which is the tunnel endpoints I'll talk a bit more about, and all the routing tables. So it's the brains for the virtual networks. So some of the spiel that VMware give, it can run on VMware, Xen, and KVM. I only ran it on VMware. It works by adding a VIB to a vDIS switch, which is pretty much a VMware kernel module that allows VXLAN, distributed logical routers, or firewalls. So traditionally, virtual switches were only layer 2. This adds layer 3 to the virtual switch, which means less east, which allows east-west traffic and not north-south, so you're not heading down to your hardware switch for routing. So I built it, and I'm like, okay, let's try these layer 2 attacks. Let's see if they work. But yeah, I don't have much to talk about that because it pretty much wasn't effective. But I did notice there was a new protocol, the VXLAN protocol, and it's like out there as one of the main additions for NSX. So I thought, oh, let's look at this. So I theorize a bit about VXLAN here and just explain it, but I don't have any demos or results for you, unfortunately, sorry. So VXLAN protocol is a standards-based overlay protocol, RFC 7348. You should go read it. It's really interesting. It leverages layer 3, so pretty much underneath everything's layer 3. We don't have to worry about spanning tree, and then it creates a layer 2 tunnel over the top. It has an increased namespace, so it has 6 million identifiers as opposed to VLANs, which are 4,094. And it's an integration of physical and virtual worlds. So this is how I see VXLAN. It's pretty much you have 2 virtual switches, you have your VTEP endpoints on each switch, and then it creates a layer 2 tunnel over the top of your layer 3 network. So it's designed for large cloud environments if you have data centers in different locations. There's VXLAN gateway type, so once you hit your VTEP, you can then move layer 2 bridging onto a VLAN tagged link. You can do VXLAN to VXLAN routing or VXLAN to VLAN routing. So, and this is what the VXLAN header looks like, which when I saw it, I was pretty excited because it's pretty simple. It pretty much is just made up of a bunch of reserved bytes and bits, and then the VXLAN network identifier is just stuck in there. It's great to write for SCAPI because you don't have to write checksums or anything, so it's really simple. So this is what VXLAN looks like in SCAPI. I don't know if it's in SCAPI now. It wasn't when I was looking at it. So pretty much the class extends the packet class. It has fields, so the flags field, it has just the default value of 8, which sets 1 for the I bit, which is what you need if you have an ID in there. Then you have 3 hex bytes, which set to 0. Then 3 bytes for the VNID, which is the VXLAN ID, and then 1 reserved byte, all set to 0 as well. So looking more at the how the VXLAN fits into the frame, because this is how you'll lay it out in SCAPI if you wanted to start trying out attacks. So the outer Ethernet contains the next hop MAC address and the source VTEP MAC address. The outer IP contains the source IP for the ingress VTEP and the destination IP for the egress VTEP. And then there's the UDP header, which has a source port of 4789, and then there's a VXLAN header, and then the rest of that is the actual frame that you're sending. So in SCAPI, you can bind layers, and this just means that when you're using it later, it will populate 4789 as the UDP destination port, which comes before VXLAN, and then after VXLAN, there's always an Ethernet field. So this is an example of using, of sending an ICMP packet in SCAPI using VXLAN. So you can see you just pretty much layer what we saw in the frame. So we have IP, UDP, VXLAN, Ether, IP, and then ICMP. That will send an ICMP encapsulated in a VXLAN header. So this would be an example of misusing VXLAN once you've got your VXLAN class in SCAPI. So in this situation, we've got IP, UDP, VXLAN, and then Ether. Then we do another VXLAN and Ether, and this is like copying off double VLAN tagging, but using the newer protocol that's come out. So theoretically, the VTEP should strip the first VXLAN header, and then what then? Like looking out for people testing this. And then another example would be just sending it straight from your VM, which shouldn't be sending VXLAN tagged frames, and where would that go? So theoretically, according to the spec and reading through the spec, there's absolutely no checking in VXLAN, so a lot of these attacks could possibly work depending on the vendor implementation. It's not just NSX that runs VXLAN, so does Cisco ACI and a few other cloud products. I think in general, just because a vendor says something is more secure doesn't mean we shouldn't test that and have a look for ourselves. So in summary, I covered off on MAC flooding, VTP, VLAN hopping, and spanning tree against virtual switches, some mitigation strategies, and then I looked at VMware NSX and the VXLAN protocol. Yeah, so thanks for having me. Thanks.